Assalamu alaikum wa rahmatullah. We are group 28 and we are pleased to present about apparent power analysis in AC circuit. And this is my group members. Me, I'm Muhammad Suleiman with matrix number AN240195. And Muhammad Afiq with matrix number CN240394. And Sayyidina bin Sauli with matrix number CN240401. I will do for introduction part. Apparent power is a key concept in AC circuits. It represents to the total power in system component real power which doesn't use full work. A reactive power which support voltage level but doesn't do actual work. The unit is voltage amplifier VA. Understanding this circle for designing efficient system, especially in industrial and renewable energy applications. By mastering apparent power, engineering can ensure better energy use, system system stability, and sustainable operations.
Next, we move on to the objective of this project. The project aims to understand apparent power in AC circuit and its relationship with shear and reactive power. We perform manual calculation and simulation using FASTEC to compare results for accuracy. The study also explore how a component like resistor, inductor, and capacitor affect power flow and emphasize the importance of power factor in designing efficient electrical system.
Problem statement. Many students and even engineers struggle to distinguishing between real, reactive, and apparent power in AC circuit. While real power doesn't actually work, reactive power supports system operation without doing useful work, making apparent power often misunderstood. This confuse affect circuit analyze component selection and energy efficiency also through and simulation result doesn't always match adding to the calculation 3-4. This project focus on apparent power to bigger the gap between classroom learning and real-world applications. The methodology. We analyze apparent power in AC circuit using both normal calculation and simulation. First, we select and modified it a simple RLC circuit, resistor, inductor, capacitor, from Sideco books powered by 230 volts and 60 Hz source. We calculate the value manual to understanding how each component affect current and power. Then we simulated the same circuit using fluorescent circuit simulation to observe real-time voltage, current and waveform behavior. Comparing both methods helped us better understanding how apparent power behavior and how components impact total power usage.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Afiq Syamil Besari, number matrix CN240394. And I will analyze this AC circuit involving resistors, a capacitor, and an inductor. The goal is to determine the total impedance, current, voltage drops, and power dissipation in the circuit. Let's break this down step by step. So the circuit consists of a capacitor with capacitance 0.33 times 10 power of negative 6 farads, and next an inductor with inductance 2.7 times 10 power of negative 3 henries. Next two resistors, R1 47k ohm, and also the same for R2 47k ohms. And lastly, an AC voltage source operating at 3 volts, and the frequency is 60 Hz. So for the calculation part, first thing first, we have to calculate the impedance of each reactive component. So step 1, we have to calculate capacitive impedance ZA. The capacitive reactance is given by Z C equals to 1 per 2 pi times value of frequency times value of capacitor. Substituting frequency 60 Hz and capacitor value 0.33 times 10 power of negative 6 farads. Then we got 1 per 2 pi times 60 times 0.33 times 10 power of negative 6 equals to 8038.1284 ohms. Next, step 2, calculating inductive impedance ZL. The inductive reactance is ZL equals to 2 pi times frequency value of frequency times value of inductor, with inductor value is 2.7 times 10 power of negative 6 henries. So the equation is 2 pi times 60 times 2.7 times 10 power of negative 6 equals to 1.0179 milliohms. Next, the total impedance Z. In total impedance Z, we got 1.0179 times 10 power of negative 3, like the as stated in inductive impedance, plus 40 resistance value 47k, or we can state as 47 times 10 power of 3. Then we get a value of 47k ohms. Then calculating step 4, calculating circuit current using Ohm's law, with value of V equals to 3 volts. We can calculate it. I equals to 3 per 47k equals to 0.0638 milliampere. Then step 5, voltage across resistors. For VR1, the equation is the value of current times the value of resistor. Then we got 0.083638 0.0638 times 47k equals to 2.9986 volt. So that is the VR1. Then the value across R2 VR2 equals to value of current 0.0638 times times the inductive impedance value 1.0179 equals to 0.0649 microvolt. Then the power, then step 6, lastly the power calculations. True power P equals to VR1 value of VR1 times current. Then the VR1 is 2.9986 times current 0.0638 equals to 0.1913 milliwatt. Yeah, milliwatt. Then reactive power VR2 value of VR2 times current. VR2 is 0.0638 times current 0.06 uh, 0. Oh sorry, VR2 is 0.0649 microvolt times current 0.0638. So we get 0.0041 0.0041 sorry NVAR. So from power triangle we get the S equal to square root 0.1913 milli power of 2 plus 0.0041 n power of 2. Then the total is 0.1913 millivolt ampere. So that is the apparent power value. Thank you.
First of all, I want to introduce myself. My name is Saidul Besauli. My metric number is CN240401. Okay, first of all, I'm gonna tell about the simulation and the explanation of this project. After we complete the manual part of the project, we move on to the simulation to check if our result makes sense and to see how the circuit would behave in real time. We use fast-start circuit simulator because it is simple, user-friendly, and allows us to build and test circuits visually. In the simulation, we build the same circuit we use in our calculation, which include a resistor, an inductor, and a capacitor, all powered by a 230 volt RMS 60 Hz supply. This simulation gave us better understanding on how current and voltage move through the circuit. We could clearly see the waveform and how the components interact with each other. It shows how the current responds when there is resistance, how the inductor delay the current, and how the capacitor affect the overall flow of power. We also look at how the circuit use power and how some of it used for real world, with some of it just move back and forth due to inductor and capacitor. One of the most useful part of the simulation was seeing the difference between the real power and the total power, which is the apparent power. It helps us to understand that even if a circuit uses a certain amount of total power, not all of it is converted into useful work. Some of it is reactive and need to be supported by the system. The value we got from the simulation were very close to our manual calculation, which means our circuit was built correctly and our understanding was on the right track. Next, I'm going to tell you about the difference between the simulate value and the calculate value. The calculate and simulate to power values are almost identical, which the simulate to power being 0.191 milliwatt and the calculated power being 0.1913 milliwatt. The close similarity show that the simulation model is a close reflection of the theoretical calculation and there is a great level of accuracy in the simulation process. Next is the difference in reactive power. There is large difference in the simulate and calculate value of the reactive power. The simulate reactive power is 0.0084 and VAR where the theoretical reactive power is 0.0041 and VAR. The reason behind the discrepancy can be different of in bodily or consideration of the reactive element inductor and capacitor in the simulation and the theoretical calculation. It can also be a representation of the assumption or simplification in the theoretical approach that are not present in the simulation. Lastly, apparent power. Both simulate and calculate apparent power value are in exact agreement with each other at 0.1913 millivolt. This also validates the correctness of simulation and theoretical method of apparent power estimation. In summary, the result demonstrate a high degree of match between the simulate and calculate tool and apparent power value, demonstrating strong and correct modeling. However, the observed difference in relative power values implies that further research is warranted to explain the cause of the difference, including verifying the simulation assumption or correctness of relative component calculation. Okay, we move on to conclusion. In conclusion, understanding apparent power were very important when analyzing AC electrical system to the project. We learned how apparent power is made up of both real power and reactive power on and how each other plays a role in how electrical circuit operate. By going through both the theory and simulation, we get a clearer picture on how apparent power affect the overall performance and stability of a system. Real power is the part that does actual work like running machine or like debug. Reactive power, on the other hand, is the energy that flow back and flow through. Component like inductor and capacitor, it doesn't do useful work, but it's still necessary to keep the system running properly. Apparent power combines both real and reactive power, giving us a full picture of how much total power is flowing to a circuit. One key thing we focused in this project was the power factor. It shows how much of the power is being used effectively. A low power factor means more energy is wasted, while a high power factor means the system is more efficient without that energy and power. Improving power factor help us reduce energy loss and make the system more reliable. By building the circuit, doing calculation and testing everything with a simulation, we saw how different components affect the power in the system. This helps us to understand how to design better and more efficient electrical system. Overall, this power gives us strong understanding of ample power and why it matters. And the knowledge we get will be very useful for future work in electrical engineering. Okay, that's all from our group. Thank you.